In this video, I wanted to talk about springs, and specifically the design of springs as a machine element. So in the PE handbook, if you search for springs, there's a whole section on them under the mechanical components header. It's one of the subsections. Now there's two types of springs. There's helical compression springs and there are torsion springs. They're in the book, they're called helical torsion springs. Each of these is going to have its own set of equations. So for helical compression springs, we have the shear stress in the wire is equal to K sub S, which is a correction factor, and times 8 times the force applied times the mean spring diameter, and that's going to be divided by pi times little d, which is the diameter of the wire, cubed. Now this Ks right here is 4 times this constant C plus 2 divided by 4 times C minus 3, and this C is big D, so the mean spring diameter over little d, which is the wire diameter. This correction factor accounts for the fact that these types of springs don't get loaded under just pure shear or pure torsion. So both of these are going to have a correction factor, and it also accounts for things like stress concentration and that sort of thing. And then another important equation is that the spring constant K equals little d to the fourth times G, which is the shear modulus of elasticity, divided by 8 times big D cubed times N. This N is the number of active coils. And that depends on the end condition of the spring. So there's a table in the book on page 175, and there's 4 types of spring endings. You can have a plane and ground, squared and closed, or squared and grounded, squared and ground. So for plane, the number of active coils, which I'm just going to call N sub A, equals the total coils. For plane and ground, the number of active coils equals the total coils minus 1. For squared and closed, it equals the total number of coils minus 2. And then the same thing for squared and ground, it's the total number of coils minus 2. But yeah, so these are all the important equations for helical compression springs. There's one other table other than the one that has the this information, this end condition information. This table has other information as well, but there is another table that tells you how to calculate the tensile strength of some common spring steels. But it depends on the material, and there's an equation for pretty much each material, but they're written out there in the book. So if you ever come across that, it should be pretty easy to figure that out. For helical torsion springs, we don't have the stress we measure isn't shear stress, it's bending stress. So the bending stress equals this KT, which is another correction factor. That's going to be times 32 times F, which is the force applied, times R, which is the radius from the center of the coil to the load, then divided by pi times little d cubed. This k sub t here equals 4 times c squared minus c minus 1 divided by 4 times c, and that whole thing times c minus 1. And again, this is just to account for the fact that it's not under pure bending. There's other forces or loads, stress concentrations in there. This c is the same as before. It's big D over little d. And then for the spring constant, we have k equals d to the 4 times E, which is the modulus of elasticity, or Young's modulus, divided by 64 times big D times N. And again, N is the number of active coils. And then, again, similarly to how with a helical compression spring, for different materials, the way you calculate the yield stress or yield strength is different for different materials. It's a little bit simpler for torsion springs. There's only 2 equations, but I don't really think we need to get into that at the moment. Another equation you might run into with helical torsion springs is about deflection. So we have F times R equals K times theta, and theta is going to be your deflection. There's also a couple equations at the beginning of the section just about springs in general, which probably would already know, but the spring force equals the spring constant times the distance, and then the energy stored in a spring equals the spring constant times the distance squared over 2. But yeah, I can go ahead and get into an example here. A helical compression spring is made from an oil-tempered steel wire with a wire diameter of 0.25 inches, a mean coil diameter of 2 inches, and then it goes ahead and gives us the number of active coils, which is 10. In a lot of questions, it will give you the total number of coils and then give you the end conditions, and you'll have to calculate out the number of active coils. And then it gives us the shear modulus of elasticity, and we are given the spring is subjected to a static load of 150 pounds, and asked to determine the spring rate K, the spring deflection under the load, the maximum shear stress in the wire, and the factor of safety against yielding if the yield strength of the material is 80 KSI under shear. Okay, so for A, we have our equation, which is the spring constant for helical compression springs equals little d to the 4 times G divided by 8 times big D cubed times N. So it's going to be 0.25 inches to the 4th times 11.5 times 10 to the 6th PSI divided by 8 times 2 inches cubed times 10. So that's going to come to 70.19 pounds per inch. So in order to get this spring to change from its free length by 1 inch, you need to apply a 70.19 pound load. For B, we're asked to find the deflection of the spring under load. So we have this equation. I guess this equation only applies to compression springs. It doesn't apply to torsional springs. Should have made that a little bit more clear earlier. But the deflection is just F over K, which is 150 pounds divided by 70.19 pounds per inch, which is going to be about 2.14 inches. Then the maximum shear stress, we're going to use our equation for shear stress, which is that is going to be equal to Ks times 8 FD, big D, by pi times d cubed. And this ks is going to be 4c plus 2 divided by 4c minus 3. So my c is going to be big D over little d, which is 2 over 0.25, which is 8. So we're going to have 4 times 8 plus 2 divided by 4 times 8 minus 3. It's going to come to 1.17. So my shear stress is going to be 1.17 times 8 times 150 pounds times 2 inches divided by pi times 0.25 inches cubed. So that's going to be 57,204.1. And it's going to be PSI. Alright, and then our factor of safety against shear is just going to be our yield strength over our actual stress. I guess it specifically says that's the shear stress, or shear strength, which was 80,000 PSI, divided by 57,204.1 PSI. So factor of safety is about 1.4. So yeah, these spring problems really aren't too bad, because it gives you all the equations you need, and it has tables if there's any other information that you might need to extract from them. But yeah, I hope this helps.